and just said we'll worry about it later. So we have a chain. In the solution I just showed, we have a chain of weak entity sets. And the way that that's interpreted in the ER diagram is the weak entity pulls in the strong entity's key, or sorry, it pulls in the supporting entity's key. So the one on the very end is going to have this really complex key because it gets bigger and bigger with each link in the chain. So ER diagram, in terms of ER diagram, that's fine, it doesn't matter. In terms of SQL in a real database, you don't want to have a really large, complex primary key. So what we can do, we can basically simplify the way that we uniquely identify one of these weak entity sets. So this entity set in the middle, we'll call it the B one, is pulling in A as part of its key. So its key would be B and A. But I'm just using unique instead of primary key to have the same meaning. Okay? And then I add a primary key, which is just some small integer identifier. The whole point, the reason I did this is now the primary key is a single integer column, whereas before it was two who knows what columns. So yes, I did add an additional column to the table, but the trade-off is that my primary key is now smaller. Okay, so then what do we do if we go further down the chain? The whole reason I did this was so that I don't have to pull in B and A over there on the far right entity. So instead of pulling in B and A, I've now kind of distilled B and A down to a smaller identifier where BID represents B and A. So I can just pull in BID instead of the full combination of its uniqueness constraint. Okay, so I have C, which is the partial key from the C entity set. Combine that with BID and make BID a foreign key. So this will hopefully make more sense with a concrete example. Here is classes from the ER diagram, or from the LMS. I filled it in, and I've stripped out some of the attributes that don't matter, but I filled it in with some example instance data here. So let's say course ID X can have an offering in fall 17 and spring 18. We can have the same semester show up as long as it's for a different course. So I can have P in F17 and so on. Okay, that was the primary key. At least if you do a straightforward translation from ER to schema. So, and then here is assignment categories. These are both weak entity sets. Assignment categories is the one on the very end of the chain. It's supported by classes. And so if we just look at this table on the right, I can have X and F17 show up twice in assignment categories, so long as the name is different. So I can have labs, tests, quizzes. The combination of the three needs to be unique. But the foreign key comes from the fact that it's a weak entity set and it had to pull in those to make up its key. So basically, these two things combined are pointing to two things combined from the supporting relationship. Okay? Now, what if I just add an ID to classes and make that the primary key and still say that the combination of the other two has to be unique? Now basically what I've done is, since the combination of these two needs to be unique in every row, and this by itself needs to be unique in every row, that basically ties every class ID to exactly one combination of course ID and semester. So I've essentially shortened the key, made it so I can uniquely identify them with a smaller piece of data. Now I can just pull that into assignment categories as the representative of course ID plus semester. Yep.
This is just when you're translating the tables, or is there a way?
Right. This is just for translating the tables. The ER diagram, you don't show it this way. You just show it's a weak entity set with a partial key.
Does it not become a normal entity? Why is this a weak entity?
There's no such thing as weak entity versus strong entity when you're talking about tables. That only applies to ER diagrams. Okay, and then further, let's say maybe somebody needs to reference assignment categories, maybe another weak entity or just anything that uses a foreign key, uses it as a foreign key. I can add another ID there, which uniquely identifies every combination of class ID plus name. So you basically take everything that needs to be unique in your own table, add a new single column unique identifier, and that now represents the other unique combinations in the tuple, so that you can export that as the foreign key instead of exporting a complex thing. Now, I want to be clear that doing this is not part of the ER model, and in fact is not required. You could do a straightforward translation to schemas and it would just work. This is an optimization to make the primary keys shorter.
So with the department example, is it like it's good practice to do the same thing with the its primary key, like an ID here, and just have the subject abbreviation?
With the department example where the primary key is a subject abbreviation, is it a good idea to add an additional key? It doesn't really matter that they have to have the same type. What matters mostly is that they're short. So the department ID turns out is going to be no more than 4 characters, 4 bytes. So that is already really small, in fact, smaller than an int, and will be, no, sorry, that's the exact same size as an int. But it's small enough that you don't need to, adding an extra int would not help to identify it. Okay. Yeah, one more.
So, I'm sorry, I feel like I might be getting more specific here, but I feel like, so we did in the ER diagram, you could have done it where they're not weak entities, and just given class primary key of class ID and assignment category of the category ID, and then that way assignment category was a strong entity.
So could you do this? Do this in the ER diagram? No, because then there's no way of showing that in the ER diagram, there's no way of showing that the combination of something from entity A plus something from entity B needs to be unique. So all this confusion comes down to the separation between ER diagram and tables. Don't think about tables at all when talking about ER diagrams, even though they do just turn into tables with keys and unique and foreign keys and stuff like that. So finally, to kind of put this together back into our abstract picture, you basically invent a key wherever there's a complex key that you need to simplify, especially if the whole thing is used as a foreign key somewhere else. Just make it shorter and then export that as the foreign key. And you can keep doing this down the line. I've only shown a chain of length 3 here. So it looks like the benefit is not that great. But if you keep going, say it was a chain of 10 or something, the single key that comes from the previous entity set in the chain is enough to uniquely identify, like represent the whole line in the chain. So the benefit pays off more and more the longer this chain gets. Okay, so back to SQL. So that was kind of a sidetrack because phase 2 is coming up, and this is just an optimization and a suggestion for how to translate your ER into tables. So back to SQL. I want to recap a little bit what we were talking about last time. So we saw that you can kind of do renaming. You can rename a relation just like you can in relational algebra. And you basically do a nested select, you put it in parentheses, and then that whole thing, you say as, and then give it a name. And then you can use that, you can join that with some other thing, or apply certain filters. Okay, so this inner thing is selecting ISBNs for, this is selecting the ISBN for Lorax, and then it's joining that, natural join, with the inventory in order to get the serial numbers of the Lorax. Yes, you could easily rewrite this query without using a nested select, but this is just to show, kind of in a basic way, how the syntax works. And then we saw we can use this to implement intersect. SQL, the language SQL does have intersect, but MySQL doesn't implement it. So you have to implement it. There are lots of ways to do it. Here's one of them. So if I select just address from corporate locations and just address from retail locations, then I can natural join those two things together. If your two relations have the same schema, then natural join is like an intersect. Because it's basically picking out all the columns that are the same and all of the values that are the same in those columns. Okay, let me ask you a question here. Why do I then need this part? So let's just look at all the rest of this. So this is the intersection of addresses between corporate and retail. Yep.
I was just going to say that you have a relation there, but you're not actually doing anything with it.
Yeah, exactly. Without this top line, all we have is a relation. We're not actually doing anything with it. So to kind of illustrate this, here's a simple SQL query. A join B. So not a query, actually. Here's a simple, what you might think is an SQL statement. This is not valid. I can't just do A join B. Like, well, what do you mean? What do you want with A join B? You have to have a select and do something with it. So that's why we need that select, even though we already have two other selects in here. Those are nested selects, and they don't actually give me anything in the end. Okay. And then we saw this in operator. So select something, select whatever from y, where x is in something. So the in operator, it applies to a condition. So, I can have where x greater than 5 or something. Where, it's a Boolean expression that it's expecting. So in returns a Boolean. This is saying if x exists in whatever is inside the parentheses here, then it results in true for that x. Okay, and then we saw that is a nice way to formulate intersection. Another way to do kind of the same thing. So select address from corporate where that address is in select address from retail. Okay. This is kind of just review so far. Any questions? It's important to recap this before we move on to what I'm going to show next. Yep. No question? And then finally, set difference. Find all locations that are corporate only. So the relational algebra is easy to formulate. The translation to SQL, we can just use not in. Okay. That just negates the in operator. Okay, and then we got to this exercise. So given the library that we've been playing with, find all patrons who have not checked out a book, and find all patrons who have checked out the Lorax and Harry Potter. So for the second one, try not to think of it in terms of division. Division is really hard to translate to SQL. We'll see how to do it, but try not to just like come up with it on the fly. Don't think of it in terms of division. The hint here is use nested selects to try to figure out kind of the, think of it kind of like an intersection. And I'll give you, we were going to do this last time. I'll give you a few minutes. Let's work on it right now with the people around you.
So not using joins, just nested selects.
You can use joins,
but with nested selects.
Yes. AJ. All I've done here is I've added some more stuff to the tables, just to kind of make things a little more interesting. You know what? For the first one, let's actually use normal library. So select star from checked out. Gives me the same thing that was on the slide. Well, you can't see it it's behind this orange box, but it is card num 1144. So who has a query for finding patrons who have not checked out a book?
So select everything from patrons.
Okay, I'm going to call it patrons P.
Yeah, where P dot checked out card numbers P dot card number not in. Then parentheses select card num from checkout.
Select a card num from
Checkout.
checked out. Okay, so yeah, let's just kind of, the best way to think about SQL queries is usually build them up from the inside out. So this last thing we did, select card num from checked out, that is patrons who have checked out a book. There might be duplicates in there, but it doesn't matter, because all we're doing is saying, is another card num in there or not? If it's in there twice, then it's fine. Okay, and then so we select everything from patrons where p.cardnum not in. And then the only slight difference is the query actually did say to give the names. So instead of selecting star, I'll just select p.name. Okay. And then, so hopefully you did think about the second query and came up with something useful. There are a lot of ways to do it. So I'm just going to show kind of my solution. So think of it in the context of what you were thinking about. So first thing I'm going to do, I'm going to build it up kind of one piece at a time. I'm going to select card num. So we want people who have checked out the Lorax and Harry Potter. I'm going to select card num from checked out. Okay. Natural join inventory. Natural join titles, where title equals the Lorax. Titles dot title. Okay. So that's part of my query. That gives me card numbers of anyone who has checked out the Lorax. I can easily change that to Harry Potter to give me card nums of anyone who's checked out Harry Potter. Now basically what I want is the intersection between this and this, which would give us an answer of 1. That would be the card num of anyone who's checked out both. So I'll start by just copying this, because I'm going to need basically 2 of them. I'm going to put it in parentheses, and I will say as Lorax. Okay. And then I will natural join that. Natural join is the way we're going to get an intersection with, paste the whole thing, change the query to Harry Potter as, I'll just call it HP. Okay. And then natural join that with patrons. Okay. All I have so far is a relation. So this is the patrons tuple for anyone who has checked out both of those books. Now I need to select something from that patron. So select name from that. Let's see, what did I do wrong? Select. Okay. So Joe is the person who has checked out both of those books. Yep.
Why do you need to name them? Like, it doesn't seem like you do something.
Why do you need to name them? You just, anytime you do a temporary nested select like that, you just have to rename them, because otherwise, so what it's doing behind the scenes to make all of these joins happen is it's actually making some temporary relations. And you can never have the same column name twice in any relation. So by renaming them, I'm telling SQL that you can call it like hp.cardnum instead of just cardnum. That unifies the column name.
So I'm assuming because you have to create 2 tables temporarily and then intersect them, that you can't use like or like when you're checking for titles, you could say the title equals the Lorax or the title equals Harry Potter.
So title equals Lorax or title equals Harry Potter would give me people who have checked out either of those books.
Right.
I want people who have checked out both of them. So if you do, and there's no such thing as a book that has both of those titles.
Okay.
Yeah. Okay, let's take a short break, and then we'll move on to something new. Pose a question to you. Here's a phones table, like a more expanded phones table from the library, where 2 different people can have the same phone number. So like maybe it's a landline at a home somewhere and the 2 people live at the same address. Okay, so I have like card nums 1 and 2 both have the 555 phone number, and 3 and 5 both have the 777 phone number. How would you write a query, either relational algebra or SQL, that finds all the people? So the people I want out of this query would be like 1, 2, saying that they share a phone number, and 3, 5. Yeah.
Use a self join.
Okay.
Select card number, phones, join phones.
Use a self join. Exactly. So that is the next topic of discussion here is you can join a table with itself. Usually you would think, why would you ever do that? You know, you already have everything in the table. Why would you need to combine it with itself? Basically, it's to get every combination of patron and other patron. Okay? So this becomes n squared. It is every single pair. Take a set of things, and then take every single pair of those things. And so we end up with this giant table with lots of stuff in it, and we have 2 card num columns and 2 phone number columns. And where the 2 people have the same, where the 2 phone columns are the same, is getting there. It's getting to the answer. But notice that we have, this is just saying that patron 1 has the same phone number as their self. Obviously they do. So we have to further look where the 2 card nums are not equal, but the 2 phone numbers are. Those are the rows that we want out of this. And that shows us that card num 1 and card num 2 are 2 of those people that share a phone number. Okay. But there's a problem here. So let's say I was trying to write this query. It would be something like phone equals phone and card num not equal to card num. So of course phone is equal to phone. It's the same thing. And of course card num not equal to card num is always going to return false because anything is equal to itself. The problem here is I have ambiguity. So the first thing we have to do, we'll work through it in relational terms first. First thing we have to do is just rename this table. So I'm just saying phones is now P1, and I have another copy of phones, which is called P2, just to give them different names. Now my column headers are unique, P1.cardnum and P2.cardnum. Okay, then I can start filtering by where the 2 phone number columns match. And then I can filter by where the 2 card numbers do not match. So let's translate this to SQL. Let me just show you the phones table. Okay, so I have basically that which was shown on the slide. If I select star from phones, join phones, this is not going to work. So it says no unique table. This is basically, SQL will not let you do this without disambiguating. So this is where another case where renaming things is required. So I'm going to do phones P1, join phones P2. So that's the first step, the disambiguation step. You just have to use these things that are called range variables. Okay. And then we can just do where P1.phone equals P2.phone and P1.cardnum not equal to P2.cardnum. Okay, so I still have a lot of extra stuff in here. What I really want is P1.cardnum, comma, P2.cardnum. So this will show me the pair of card nums that share a phone number. So I get 2 and 1, 1 and 2, 5 and 3, 3 and 5. Now, filtering that down further so that you don't get the same combination showing up in the opposite order is considerably more tricky. We won't really go through it right now, but this is showing, okay, person 2 shares a phone number with person 1, and person 1 shares a phone number with person 2. It's all the information we want is there. Phones P2 versus phones as P2. The as is used after a nested select, or if you want to rename an individual column in your select. Does it break here? So if I did from phones as P1, so yep, still kind of the same. You need to use as in some places. It's implied when I'm doing it to rename a relation from a select like that. Yeah. Okay. So speaking of So in a self-join, we have to use this renaming because, I mean, just to kind of more clearly illustrate that, like, how would I write this query? P1.phone equals P2.phone. How would I write this query if I didn't rename it? Phone equals phone, like which one is which one? So SQL requires that if you're doing a self-join. Okay, so speaking of joins, every join we've seen so far, even a self-join, is called an inner join. So X join Y, where condition, X natural join Y, and it's equivalent to actually specifying the word inner join or the shortcut, the comma syntax, X, comma, Y. All of this is inner join. But there's something called an outer join, and there are two forms of it. There's outer left join and outer right join. You don't have to specify outer. You can just say X left join Y. That's an implied outer join. And then you have to use the on keyword. So remember, we saw way back, on is kind of another way of specifying a condition that you want to join on. You can use where. You can also use on. You have to use on if it's an outer join. So what this does is it gives all of the rows where the condition matches, kind of like the joins that we've seen, but then it also just gives you every row from the left table, even the ones that don't match. So you're guaranteed you will have at least one copy of every tuple from the left table combined with any copy from the right table where the condition is met. And then a right join is kind of just the opposite. You're guaranteed to get every tuple from the right table plus some of the ones from the left table. Okay. So let's look at patrons and checked out. If I were to do patrons left join checked out, and let's say the condition is where the cardinals match, like a left natural join. So I would get like Joe 1, 1001, Joe 1, 1004, Dan 4, 1005, and then I would also get Ann 2 and Ben 3, but I can't have like a non-rectangular table. So it fills those in with null, where there's no match. Yep. How do you express that it's not null? So if I added to my condition where the right columns can't be null, yeah, then that would be one way of filtering out these rows. Yeah.
Which would be the same as inner join.
Which would be the same as inner join.
Yeah.
Okay, we can do natural left join. So I don't have to say where left column and left cardinum equals right cardinum. But there is a difference here in that, remember, a natural join is always going to distill down to just one copy of the natural column. So I don't have, like I had here, I have a cardinum column that contains some nulls where there was no match. I don't get that if I do a natural left join. I only get the serial number is null. Okay, so quiz for you. We've seen a way to find patrons who have not checked out a book using not in. Let's do it just using a left join. And let me kind of go back and just look at this table for a second, at these three tables. Okay, there is enough information here to figure out who has not checked out a book. How do we do it? Yeah, so wherever these columns from the right side of the left join are null, that's where somebody has not checked out a book. So let's try it. Let's select name from, what do I want? So how do I want to do this? Do I want, it does matter which one is on the left. Which one do I want on the left? Patrons or checked out? Patrons, left join, checked out. And I didn't do a natural, so I'll have to do where patrons.card, sorry, this has to be on patrons.cardnum equals checkedout.cardnum. Where checked out dot, let's use serial, and then I'll do equals null. And I get the empty set, which is wrong. There are people in here who have not checked out books. So here is the issue. You can't use equals on null, you have to use is. So SQL is kind of weird in that way. Like normally, in C, in Java, you can compare something to null using the comparison operator. In SQL, null is a special value where it doesn't exhibit the reflexive property, meaning it's not equal to itself. And in fact, it's not equal to anything. So null is not equal to null. If you said null equals null, the result would also be false. So you don't use the Boolean comparison operators whenever you're dealing with null. You use is or is not null. So any Boolean comparison operator where null is one of the operands, the answer is null. So let me actually just kind of show, we can do select null equals 5. Answer is null. Select null equals null. Answer is null. So that's not a Boolean. Select null is null. Answer is true. Okay. So you have to be aware of that. You're going to get really weird bugs, like unexpected results, and it'll come down to trying to use a Boolean comparison on null. So anytime I'm expecting a Boolean, but if the result is null, so it's not 0 or 1, the result is null, that's treated as false. So in other words, like any comparison on null is going to be, in some way, it's going to be considered false. Okay. So I want to go into a little more detail on these nested conditions using like a nested select. So this is different from what I did before, where I used a nested select and renamed it using as. When it shows up in one of these Boolean operators, it works a little differently. So select x from y where x in something. So remember, where is like, it's expecting some condition. So it could be x greater than 5, x equals whatever. So x in something is a Boolean operator. And there are several of these. So it's not just in and not in. There's exists, there's x op any, and x op all. So the syntax here is x is a value, and a is a multiset. So all of these a's that show up here, those are multisets. Multiset just meaning it can contain duplicates, right? Because the result of a select can contain duplicates. So you usually do have, whatever these a's are here, those will usually be from a nested select. That's just usually how these operators are useful. So what these mean, we've seen x in A. This means it results to true for that x if the x shows up in the multiset. Okay, so exists results to true if, for that x, if whatever A is non-empty. So if there's one row in it, or more than one row, then it results to true. X op any, so whatever that op is, could be like greater than, less than, or equal. This means it's true if there is some y in A such that x op y, I guess what's missing here is y, x op y, any x op y all. Just kind of like, is there some y that satisfies that, or is that operator satisfied for all y? Okay, so let's look at, let's do an example. So find all students not enrolled in databases. We've kind of seen something like this. I'll skip over this one to get to a more interesting one based on these new operators we've seen. Find all students younger than everyone in databases. Okay, so here are the two people in databases, Harry and Hermione. So all students who are younger than both Harry and Hermione. So Ron is not, because he's as old as Hermione. Malfoy is. His birth year is greater than, which means he's younger. Okay, so how do we find all students younger than everyone in databases? Let's kind of build this query up. So I'm going to start with select. I have to switch over to a different database. So there are enrolled students and courses. I'm going to start by selecting date of birth from students, natural join enrolled, natural join courses, where courses.cname equals databases. Okay? So what this gives me is a multiset containing the dates of birth of everyone who is in databases. Now I need to find everyone who is younger than all of those birth dates. So starting with what I had there, okay. So remember, it's best to think of them, build them from like the inside out. We can now select, I'll kind of use some renaming here, s2.studentName from students s2, and I'm just doing that because I have two students showing up in this query, where s2.date of birth greater than all of those dates of birth. So why greater than if we're looking for people who are younger than all of them? Because we're using the birthday. So a greater birthday means you are younger. You just kind of have to keep that in mind when you're dealing with date comparisons. Okay. Any questions before we wrap up? Yes?
Can you do an order by? Just order by birthday?
Order by, so if you did order by birthday, yes, you still kind of have to do this additional query that filters it down to just the students that are in databases. Order by really only shows you, yes, so you could do order by and then is it greater than just the first one in that? That's, yeah, kind of another way you could work that. Okay, We'll see you next time.